Welcome to the Deep Sleep Science Channel. Tonight, we're drifting gently across a quiet red world where giant volcanoes rise higher than any mountain on Earth and canyons stretch so far they could swallow entire countries. We'll wander through a planet where sunsets glow blue instead of red, where ancient rivers once carved valleys now frozen in time, and where tiny robots explore in complete silence beneath a dusty sky. As you relax, you'll discover how Mars slowly changed from a wetter, warmer world into the cold and mysterious place we see today. One layer, one story, one quiet detail at a time. So settle in, get comfortable, and if you enjoy these calm journeys, you might like to leave a like, subscribe, or share a comment before you drift off into sleep. Mars is home to Olympus Mons, the largest volcano in the entire solar system. It is not just a little bigger than volcanoes on Earth, but vastly larger, rising so high above the surrounding land that it makes even Earth's greatest mountains seem modest by comparison. Mars also holds Valles Marineris, the largest canyon system in the solar system. This is not a single narrow crack in the ground, but a giant network of enormous chasms stretching across a huge portion of the planet, showing just how dramatically the Martian crust has been shaped. One of the loveliest surprises about Mars is that its sunsets can glow blue near the sun. On Earth, sunsets usually turn red and orange because of the way our thicker atmosphere scatters light. But on Mars, the fine dust in the air changes the effect and creates a very different evening sky. Mars has two small moons, named Phobos and Deimos. Unlike Earth's large round moon, these companions are tiny, irregularly shaped, and more like captured space rocks or battered fragments than polished globe-like worlds. Today, Mars has no global ocean covering its surface. That makes the planet look dry and stark, but it also makes the evidence for its wetter past even more striking, because the world we see now is so different from the world it seems to have once been. At both the North and South Poles, Mars has polar ice caps. These frozen regions are among the clearest signs that water and ice still matter on Mars, even though the planet now appears cold, dusty, and desert-like. Mars once had environmental conditions that were much more favorable to liquid water than the planet has today. That means early Mars may have been a very different place, with a climate and surface conditions that allowed water to remain stable long enough to shape the land. Jezero Crater was chosen for exploration partly because it preserves an ancient delta built by flowing water. A delta forms where moving water slows down and drops sediment. So this crater records the quiet work of an old river system feeding into a basin long ago. NASA MAVEN mission helped explain how Mars changed from a warmer, wetter early world into the colder, drier planet we see now. That transformation is one of the central stories of Mars, because it helps scientists understand how a planet can change so deeply over billions of years. Data from the InSight mission showed that Mars has a molten core. Even though Mars may seem silent and frozen from the outside, deep within the planet there is still a liquid metallic region at its center, which tells us that its interior is more active and complex than it once seemed. InSight also confirmed that Mars experiences Marsquakes. These are real seismic events, similar in principle to earthquakes, and they reveal that Mars is not just an ancient rock sitting perfectly still in space, but a world that still shifts and trembles. Mars became the first planet beyond Earth where powered, controlled flight was achieved. The tiny helicopter Ingenuity showed that even in the extremely thin Martian air, flight is possible if the aircraft is designed carefully enough and its blades spin fast enough. The robotic explorers sent to Mars have transformed it from a reddish point of light in the night sky into one of the most familiar alien landscapes humans have ever studied. Instead of guessing from far away, we now have close-up views of rocks, dunes, sunsets, and ancient river deltas. Mars is one of the most topographically dramatic planets in the solar system. Its enormous volcanoes, giant canyon system, and vast differences between high and low regions give it a landscape shaped on a scale that is difficult to fully imagine. Its ancient lakebeds and deltas make Mars one of the strongest places in the solar system to search for preserved records of past habitability. These places are important because water can leave behind minerals, layers, and textures that record what conditions were once like. Its accessible ice reserves make Mars valuable not only as a subject of science, but also as a practical target for future exploration. Water ice can matter for drinking water, oxygen production, and even fuel making. So these frozen deposits are more than just geological curiosities. Mars keeps surprising scientists because each mission adds a new layer of detail instead of simply repeating what was already known. That is one reason the planet remains so compelling. Every closer look tends to reveal something more complicated, more subtle, or more unexpected. For a planet with no oceans, no forests, and no cities, Mars has produced one of the richest stories in planetary science. It has become a place where geology, climate, atmosphere, history, and the search for past habitability all come together in one world. Its atmosphere is thin enough that gases can be lost to space over time, yet it is still active enough to create seasons, raise dust storms, and produce blue sunsets. Mars shows that even a delicate atmosphere can still shape the daily appearance and long-term evolution of a planet. Mars is the fourth planet from the Sun. That position places it just beyond Earth in the solar system, close enough to have long captured human attention, yet far enough away to be a colder and more distant world. It is the seventh largest planet in the solar system. Mars is not one of the giants, and it is much smaller than Earth, but it is still large enough to have a layered interior, an atmosphere, polar caps, moons, and an extraordinary variety of surface features. Mars is a terrestrial planet, which means it has a rocky body rather than a deep outer envelope of gas. In this way, it belongs to the same broad family as Earth, Venus, and Mercury, with a solid surface and a crust that records its long history. Mars formed about 4.5 billion years ago as the solar system settled into its present arrangement. So when we look at Mars, we are looking at a world that has existed since the very early era of planetary formation. It is often called the red planet because iron-rich dust on and above the surface gives it its reddish appearance. That famous color is not just a trick of distance, but a real property of the dusty material spread across the planet. Up close, though, Mars is not only red. Its surface also shows browns, golds, and tans, so the planet has a more varied and earthy palette than its simple nickname might suggest. Mars is about half the diameter of Earth. That smaller size affects many things, including its gravity, its ability to hold onto atmosphere over time, and the scale on which mountains and volcanoes can grow. Even though Mars is smaller than Earth, its total surface area is close to the amount of dry land on Earth. That means that, in terms of sheer ground area to explore, Mars offers a surprisingly vast landscape. A Martian day is called a sol. This special word is useful because a day on Mars is not exactly the same as a day on Earth, and missions operating there often organize their work according to Martian time. One sol lasts 24 hours, 39 minutes, and 35 seconds. So a day on Mars feels almost familiar in length, but it stretches just a little longer than a day here on Earth. Mars is tilted on its axis by about 25 degrees, which is fairly close to Earth's axial tilt. That tilt is important because it is what allows Mars to experience changing seasons rather than staying in one constant state all year. Because of that tilt, Mars has spring, summer, autumn, and winter. Even though the climate is far colder and drier than Earth's, the planet still moves through a repeating cycle of seasonal change. A year on Mars is much longer than a year on Earth, because Mars takes more time to travel once around the Sun. Its greater distance means its orbit is larger, and that makes the full trip take longer. Mars also follows an orbit that is more stretched out, or more elliptical, than Earth's. So its distance from the Sun changes more noticeably during the year, which has important effects on climate and season length. Because the orbit is more elliptical, the seasons on Mars are unequal in length. Some last noticeably longer than others, so the Martian year is not divided into 4 evenly balanced quarters. The northern and southern hemispheres experience opposite seasons, just as they do on Earth. That means the 2 poles of Mars can be in very different conditions at the same time, with one growing colder and darker, while the other becomes brighter and warmer. The length of daylight on Mars changes with both season and latitude. Near the equator, the pattern is gentler, while nearer the poles, the changes become much more dramatic over the course of the Martian year. Any calendar made for Mars has to account for both sols and a much longer year. That makes timekeeping on Mars a little more complicated, because it has to follow a rhythm that is familiar in some ways and different in others. Mars has a very thin atmosphere. Compared with Earth's thick blanket of air, the Martian atmosphere is sparse and delicate, which shapes nearly everything about the planet's weather and surface conditions. That atmosphere is made mostly of carbon dioxide. So the air on Mars is very different from Earth's, and it cannot support human breathing without life support systems. Nitrogen is the second most abundant major gas in the Martian atmosphere. It is present in much smaller amounts than carbon dioxide, but it is still an important part of the overall mix. Argon is the third most abundant major gas in the Martian atmosphere. This makes Mars's air chemically simple in broad outline, though scientists continue to study even its tiny trace components. The average surface pressure on Mars is less than 1/100th of Earth's average surface pressure. In practical terms, that means the air presses down only very weakly on the surface compared with what we are used to. Because the pressure is so low, liquid water is unstable at the surface under most present-day Martian conditions. Even if ice melts for a moment, the water does not usually remain as a stable liquid for long. The thin atmosphere makes Mars a cold world overall. Without a thick atmospheric blanket to trap heat efficiently, warmth escapes more easily and temperatures stay low across much of the planet. The average surface temperature on Mars is about -53 degrees Celsius. Of course, that number can vary from place to place and season to season, but it gives a clear sense of how cold the planet usually is. Temperatures on Mars can swing widely, from bitter cold polar nights to relatively milder afternoons near the equator. This large range is another result of the planet's thin air and dry surface conditions. Mars does not have breathable air for humans. Anyone visiting the planet would need technology to provide pressure, oxygen, warmth, and protection from the harsh environment outside. Even though the air is thin, Martian winds can still move dust. Over time, those winds help shape dunes, lift fine particles into the sky, and change how the surface looks from one season to the next. Mars can experience local dust storms, regional dust storms, and at times even dust events that spread around the whole planet. These storms are among the most powerful and distinctive weather patterns known on Mars. Dust devils are common enough on Mars that orbiters high above the planet and rovers moving across the ground have both photographed them. These spinning columns of dust show that even with such a thin atmosphere, Mars still has active weather that can lift loose material into twisting, moving shapes. Fine Martian dust is very easy to lift, and once it rises into the air, it can stay suspended for a long time. Because the particles are so small and light, they do not fall back quickly, and this helps explain why the sky, weather, and visibility on Mars can change so much. Dust in the Martian atmosphere affects both temperature and the color of the sky. In a simple way, the dust acts like a filter and a blanket at the same time, changing how sunlight moves through the air and how heat is absorbed and released. The blue color seen near the sun at Martian sunset is caused by the behavior of fine dust, not by thick blue air or large bodies of water. The tiny particles scatter light in a different way from Earth's atmosphere, so the effect looks unusual but follows real physical rules. Curiosity captured the first color sunset sequence from Mars in 2015. That mattered because it gave scientists and the public a more realistic sense of how evening light behaves on another planet, turning something once imagined into something directly observed. Pathfinder had already returned true-color sunset views from Mars back in 1997. Even early missions were able to show that the Martian sky changes in beautiful and scientifically meaningful ways as the sun drops lower. During the daytime, the sky on Mars can look butterscotch or pinkish because of the dust floating in the air. So although Mars is often imagined as having a plain dark sky, the real view is softer, hazier, and more colored by suspended particles. The polar caps of Mars contain large amounts of water ice. This is one of the clearest signs that water still exists on the planet in major quantities, even if it is mostly locked away in frozen form rather than flowing freely on the surface. Parts of those polar caps also contain frozen carbon dioxide, which is often called dry ice. So the Martian poles are not made of only one kind of frost, but of a changing mixture that reflects the unusual atmosphere and climate of the planet. The size of the polar caps changes with the seasons because carbon dioxide can freeze out of the atmosphere in colder periods and then turn back into gas later. This means the shape of the poles actually responds to the rhythm of the Martian year. The seasonal growth and retreat of polar frost is one of the most obvious repeating cycles on Mars. It is a large, visible sign that Mars is not frozen into one unchanging state, but continues to breathe in a planetary way through regular seasonal shifts. If all the water currently locked in Martian ice were melted and spread evenly over the planet, it would cover the surface to a depth of roughly 30 meters. That is a powerful way to picture how much frozen water Mars still holds, even after so much of its wetter past has vanished. Water ice is not limited to the poles. Mars Express found large amounts of it in the shallow subsurface of high-latitude regions, which means ice can lie hidden beneath the ground, where the surface itself may look dry and dusty. Mars Express also reported evidence for buried water ice much closer to the equator than scientists once expected. This was important because it suggested Mars may store useful ice in regions that are warmer and easier to reach than the deep polar zones. Some equatorial deposits may contain layers of water ice several kilometers thick beneath a covering of dust or ash-like material. In other words, Mars may hide huge, frozen reserves under surfaces that do not immediately look icy at all. The distribution of water on Mars is not simple. It includes polar ice, shallow ground ice, hydrated minerals, and water vapor in the atmosphere. So the story of Martian water is spread across the sky, the soil, the rocks, and the poles. Orbital observations have found minerals that form in the presence of water. These minerals act like evidence preserved in stone, showing that water once interacted with the surface and changed the chemistry of rocks in lasting ways. Ancient valley networks on Mars suggest that liquid water once flowed across parts of the surface. These branching patterns resemble drainage systems, and they are difficult to explain without water moving downhill over long enough periods to carve the land. Some ancient deltas and lakebed sediments show that water on Mars was not always brief or fleeting. In certain places, it seems to have remained stable long enough to transport sediment, build layers, and reshape entire local landscapes. Gale Crater, explored by Curiosity, contains layered rocks that record long-lived ancient lake environments. These rocks are important because they preserve a sequence of conditions, almost like pages in a very old natural history book. Hydrated minerals on Mars act as geologic records of water that existed long ago. When scientists study them, they are not just learning what rocks are made of, but also what kind of environment must have been present for those rocks to form. Mars's water story is not only about lakes sitting on the surface. It also includes groundwater below the land, ice frozen in place, and water chemically locked into minerals, making the planet's history far richer than a simple wet versus dry picture. Modern Mars still has a water cycle, but it is dominated by ice and vapor rather than rainfall and seas. Water moves through the system in quieter, colder forms, rising and settling in ways very different from Earth's familiar rain and rivers. Dust storms can raise water molecules higher into the atmosphere, and that can increase water loss to space. So dust is not just a surface nuisance or a sky effect. It can also influence the long-term drying out of the entire planet. NASA MAVEN mission studies how Mars loses atmospheric gases to space. This is a central question in understanding Mars because a planet's atmosphere helps shape climate, surface pressure, temperature, and whether liquid water can remain stable. One reason Mars lost so much of its atmosphere is that it no longer has a strong global magnetic field like Earth's. Without that broad protective shield, the planet became more vulnerable to the action of the solar wind over immense spans of time. Without a strong global magnetic shield, the upper atmosphere of Mars is more directly exposed to the solar wind. That means charged particles from the Sun can interact more strongly with the planet's outer gases and help strip some of them away. MAVEN observed atmospheric escape processes that are actively removing gases from Mars even today. So the thinning of the atmosphere is not only an ancient event from the distant past, but something that still continues in measurable ways. One of those escape processes is called sputtering. In simple terms, energetic particles strike atmospheric atoms with enough force to help knock them away into space, almost like repeated tiny blows, gradually wearing something down. MAVEN also detected auroras at Mars. This showed that glowing atmospheric events are not limited to planets with Earth-like magnetic behavior, and that Mars has its own more unusual form of interaction between atmosphere and solar activity. In 2018, MAVEN reported the first observation of a proton aurora at Mars. That was an especially important discovery because it revealed a type of auroral activity produced through a different process than the most familiar auroras seen on Earth. Some Martian auroras are seen in ultraviolet light rather than in the bright visible colors people often associate with auroras on Earth. This means they can be scientifically important while remaining invisible to the human eye without special instruments. NASA describes Mars as having a hybrid magnetosphere rather than a strong planet-wide magnetic field. This helps explain why Mars does not behave like a simple, smaller version of Earth, but instead has a more patchy and unusual relationship with space weather. Mars has a dense core at its center. Even though we cannot see it directly, the behavior of seismic waves lets scientists infer that deep inside the planet, there is a heavy central region influencing its internal structure. NASA describes that core as being made mainly of iron, nickel, and sulfur. Those materials are important because they help determine the core's density, its behavior under pressure, and the thermal history of the planet as a whole. InSight found that the Martian core is larger than many scientists had expected before the mission. Discoveries like that matter because even a change in estimated core size can reshape ideas about how the whole planet formed and cooled. NASA reported the radius of the Martian core at about 1/800 kilometers. Putting a number on it made the hidden center of Mars feel less abstract, turning a rough idea into a measured part of the planet's anatomy. Around the core lies a rocky mantle. This mantle is the thick middle layer of the planet, and it helps connect the deep metallic center to the outer crust that spacecraft can observe more directly. Above the mantle lies a crust made of elements including iron, magnesium, aluminum, calcium, and potassium. This crust is the outer shell of Mars, and its composition helped shape the rocks, minerals, and landscapes seen across the surface. InSight showed that the crust beneath the lander is thinner than some earlier expectations. This reminds us that spacecraft do not just confirm theories. Sometimes they reveal that a planet is built a little differently than scientists had imagined. NASA reported that the crust beneath InSight is about 25 to 40 kilometers thick and divided into 3 internal layers. That layered structure suggests a more complex outer shell, with different stages or styles of formation recorded one above another. Seismic waves from Marsquakes allow scientists to study the interior of Mars without drilling deep into the planet. As those waves travel through different materials, they change speed and behavior, carrying information outward like a natural scan. InSight was the first mission dedicated specifically to studying the deep interior of Mars. Earlier missions looked mostly at the atmosphere, surface, or visible geology, but InSight focused on what lies hidden below. The lander carried a very sensitive seismometer. This instrument was designed to detect extremely subtle vibrations, because the clues to Mars's inner structure arrive as faint movements traveling through the ground. Marsquakes can be caused by faulting, volcanic processes, or meteoroid impacts. That means the shaking recorded on Mars does not come from only one source, but from several different kinds of planetary activity. Some of the largest seismic signals recorded by InSight were tied to impact events. This is especially interesting because it links what happens on the surface, like incoming space rocks, to what can be learned about the deep interior. Mars is seismically active enough that its interior is not simply a dead, perfectly still shell. The planet may be quieter than Earth in many ways, but it still has enough internal motion to produce detectable geological signals. Seismic data show that the crust, mantle, and core of Mars all affect how quake waves travel. In other words, each internal layer leaves its own signature on the motion of those waves, allowing scientists to separate one region from another. InSight's results have improved estimates of both the thickness of Mars's crust and the composition of its deep interior. This has made the internal picture of Mars much sharper and more grounded in direct measurement. NASA has used InSight findings to suggest that ancient impact debris may still be scattered through parts of Mars's mantle. That means the deep interior may still carry traces of violent events from the solar system's early era, hidden far below the surface. InSight was the first mission ever dedicated specifically to studying the deep interior of Mars. Earlier spacecraft had taught us a great deal about the surface, the atmosphere, and the broad shape of the planet. But InSight was designed to answer a quieter question: what is happening far below the ground, in places no wall camera can see? To do that work, InSight carried a very sensitive seismometer. This instrument was made to detect extremely small vibrations in the Martian ground, because even the faintest shaking can reveal what kinds of layers lie deep below the surface. Olympus Mons rises more than 25 miles above its surroundings. That is such an extraordinary height that it is difficult to compare it directly to familiar mountains on Earth. because it towers over the Martian plains on a scale that feels almost planetary rather than local. In another common measurement, Olympus Mons is described as being about 26 kilometers high. Whether expressed in miles or kilometers, the point remains the same. This volcano is one of the grandest individual landforms known anywhere in the solar system. The base of Olympus Mons is more than 600 kilometers across. So this volcano is not only tall, but also incredibly broad, spreading outward over a region so large that standing on one part of it would not give you any real sense of its full size. NASA has compared the area covered by the base of Olympus Mons to the size of Arizona. That comparison helps make the scale more understandable, because it shows that this is not a mountain in the ordinary sense, but a volcanic structure that covers a vast section of the planet. Olympus Mons is a shield volcano, built by many repeated lava flows rather than by one huge explosive eruption. Over time, layer after layer of fluid lava spread outward and hardened, slowly constructing this immense volcanic rise. The flanks of Olympus Mons are bordered by impressive escarpments and surrounding deposits linked to the volcano's growth and collapse. These features show that even giant volcanoes do not simply rise in a smooth and permanent way, but can shift, spread, break, and leave clues along their edges. Mars has several other enormous volcanoes besides Olympus Mons, so the planet's volcanic story is not centered on just one giant mountain, but on a broader volcanic province that reshaped entire regions. Arsia Mons, Avonis Mons, and Ascrius Mons form a major volcanic chain called the Tharsis Montes. These three huge volcanoes stand like a striking row of giant peaks, each one helping define the character of the Tharsis region. The broader Tharsis region is a giant volcanic and tectonic rise dominating a huge part of Mars. It is not merely a collection of isolated mountains, but a massive, uplifted area that has influenced the structure and appearance of the surrounding crust. Valles Marineris is about 4,000 kilometers long. That enormous length means it stretches across a huge part of Mars, making it less like a single canyon and more like a planetary scale system of connected chasms. At its widest, Valles Marineris reaches about 600 kilometers across. In some places, the canyon becomes so wide that it would feel more like looking across a vast broken region of crust than peering into a narrow valley. The deepest parts of Valles Marineris drop more than 10 kilometers from rim to floor. That depth gives the canyon an overwhelming vertical scale, with walls and slopes that far exceed what people usually imagine when they hear the word canyon. NASA notes that Valles Marineris is more than 10 times longer and wider than Earth's Grand Canyon. This comparison helps show that Mars did not merely produce a larger version of a familiar landform, but something truly immense and exceptional. The canyon system is named after the Mariner 9 mission team. That name quietly links one of Mars's greatest surface features to one of the missions that helped reveal the planet in far greater detail than ever before. Large landslides and slumps have modified parts of Valles Marineris over time. So the canyon is not just a giant crack left unchanged, but a landscape that continued to collapse, shift, and reshape itself after its initial formation. Valles Marineris records not only erosion, but also tectonic stretching and crustal collapse. This means the canyon's history is not explained by one process alone, but by a combination of deep structural forces and later surface change. The contrast between the giant volcanoes of Tharsis and the giant canyon system nearby shows how strongly Mars's crust has been reshaped. In one broad region, the planet displays both immense uplift and immense breaking, as if the outer shell of Mars was pushed and pulled on a monumental scale. Mars combines volcanoes, tectonic features, impact craters, and erosion in the same planetary landscape. This mixture is one reason the planet is so scientifically rich, because many major geological processes are preserved together in one world. Impact craters are among the most common landforms on Mars. They appear across the planet in great numbers, recording a long history of collisions with meteoroids and asteroids over billions of years. The southern highlands of Mars preserve especially ancient, heavily cratered terrain. These old surfaces act like long-lasting records from the early solar system because so much of their battered appearance has survived through time. The northern lowlands are smoother in many places than the southern highlands. This contrast is one of the clearest signs that different parts of Mars followed different geological histories and were reshaped in different ways. Some buried impact basins in the northern lowlands were later hidden by younger materials. So not every ancient scar remains visible at the surface, because later deposits can cover older structures and partly erase them from view. The strong difference between the high southern terrain and the lower northern terrain is one of Mars's biggest global topographic patterns. It is such a major feature that it shapes how scientists think about the planet's early history and crustal development. Mars has dunes, ripples, and other wind-shaped landforms created by the movement of sand and dust. These features show that even now, with no rivers actively flowing across most of the surface, the landscape is still being gently worked by moving air. Wind is one of the major modern surface-shaping forces on Mars. In the absence of abundant flowing liquid water today, the atmosphere and the dust it carries play a leading role in changing the appearance of the ground. Some Martian rock layers show repeated deposition, burial, and later erosion over very long spans of time. That means the planet's surface is not a simple frozen snapshot, but a record built in stages, with older layers covered and uncovered again. Mars has ancient channel systems that look like they were carved by flowing fluids. These channels are important because they suggest that the surface was once shaped by moving material in a way very different from the dry conditions we usually see today. The geology of Mars preserves evidence from very different eras, from early wet environments to later dry and dusty conditions. In that sense, the planet is like a layered archive of climate and surface change. Both Martian moons were discovered in 1877 by Asaph Hall. Their discovery added new detail to humanity's picture of Mars and showed that the planet, like Earth, also has natural companions circling it. Phobos is the larger of Mars's two moons. Even so, it is still very small compared with Earth's moon, which makes the Martian moon system feel unusual and somewhat delicate. Deimos is the smaller Martian moon. Its tiny size helps explain why it appears faint and modest compared with the more familiar large moons of the solar system. Both moons are irregularly shaped rather than round like large moons such as Earth's moon. They look more like battered chunks of rock than neatly formed spheres, which gives them a very different character from larger planetary moons. NASA says the moons may be captured asteroids or debris left from early solar system formation. In either case, they may preserve clues about how small bodies were moving, colliding, and settling in the early history of the Martian system. Phobos orbits so close to Mars that in some places on the surface it cannot always be seen. Because it travels near the planet and low across the sky, local geography and viewing position can affect whether it appears at all. Phobos circles Mars about 3 times during each Martian day. This fast motion makes it a very unusual moon, because instead of drifting slowly across the sky over long periods, it moves with surprising speed. Deimos orbits farther from Mars and appears to move more slowly across the sky than Phobos. Its greater distance gives it a calmer, more gradual motion when compared with the rapid path of its larger sibling. Mars has no rings today. When we picture Mars, we usually see a bare reddish planet with two tiny moons, not a ringed world like Saturn. Phobos is slowly spiraling inward toward Mars. Its orbit is not stable forever, and over immense lengths of time, the moon is gradually drawing closer to the planet it circles. The inward drift of Phobos is about 1.8 meters every 100 years. That is a very small change on human timescales, but across millions of years, it becomes enough to alter the future of the Martian moon system. In roughly 50 million years, Phobos is expected either to crash into Mars or to break apart. This gives the moon a kind of long-term instability, showing that not every planetary system remains unchanged forever. If Phobos breaks apart before impact, Mars could temporarily gain a dusty ring. So although Mars has no rings now, it may one day wear a faint ring made from the remains of its own moon. Phobos has been studied in unusual detail by Mars Express. Careful observations of this moon help scientists understand not only the moon itself, but also the broader history of the Martian system. Studying Mars's moons matters because they preserve clues about that system's history. Their size, shape, composition, and motions may all help answer questions about capture, impact, debris, and the way small bodies behave near planets. The tiny size of Phobos and Deimos means they exert only weak gravity compared with large moons. This week, Paul helps explain why they are so different in physical presence and influence from moons like our own. Their shapes and surfaces make them look more asteroid-like than planet-like. This resemblance is one reason scientists have long considered the possibility that they may be related to captured small bodies. A future ring formed from Phobos would make Mars briefly resemble a ringed planet, even though it has none now. It is a strange and interesting reminder that planetary appearances can change over vast spans of time. Mars's moons are among the most unusual regular companions of any major planet because they are both so small and irregular. They make the Martian system feel unlike the moon systems of Earth or the giant planets. Ancient human observations of Mars go back more than 4,000 years. Long before spacecraft, long before telescopes, people were already watching this reddish point of light and giving it meaning in their own sky traditions. Because Mars is bright and reddish, it has been tracked by many cultures since antiquity. Its color and motion made it stand out among the stars, helping it become one of the most noticed and remembered objects in the night sky. Mars is named for the Roman god of war. That name comes from its reddish appearance in the sky, a color that ancient observers connected with blood, battle, and force, long before anyone knew the planet was a cold desert world covered in dust. Before spacecraft visited Mars, telescopic views often led people to mistaken ideas about canals, vegetation, and even possible advanced life. The planet was close enough to see as a real world, but distant enough that small details were blurred, and that gap between visibility and certainty left plenty of room for imagination. Modern spacecraft transformed Mars from a blurry reddish disk into a mapped world filled with named mountains, valleys, layered rocks, dunes, and craters. Instead of guessing from faint surface markings, scientists could finally study actual landscapes in detail and begin building a much clearer history of the planet. Mariner 4 flyby in 1965 returned the first close-up images of another planet. That was an extraordinary moment in space exploration because it marked the first time humanity saw the detailed face of a distant planetary world, rather than only a small glowing disk through telescopes. Those Mariner 4 images showed a cratered landscape and changed earlier expectations that Mars might look far more Earth-like. The pictures suggested a harsher and older world than many had hoped for, and they helped shift Mars from fantasy into measured science. Mariner 9 later became the first spacecraft ever to orbit another planet. That achievement opened the door to a much deeper kind of exploration, because orbiters can study a world repeatedly over time, rather than catching only a brief passing glimpse. Mariner 9 revealed enormous volcanoes and canyon systems hidden below dust and haze. It showed that Mars was not simply a small, battered desert planet, but a place of huge geological structures that rivaled or surpassed anything known on Earth. The history of spacecraft exploration has shown that understanding Mars requires returning again and again with better cameras, better instruments, and better questions. Each mission has added a new layer of insight, often changing the meaning of what earlier missions first discovered. Viking 1 and Viking 2 landed on Mars in 1976. These missions were major milestones because they did not only orbit the planet, but also reached the surface and began studying Mars directly from the ground. The Viking landers carried biology experiments designed to test Martian soil for possible signs of life-related activity. These experiments became famous because they pushed Mars science beyond geology and weather into one of the biggest questions of all: whether life had ever taken hold there. Viking also provided the first long-lived surface weather observations from Mars. That meant scientists could begin tracking Martian conditions not just as isolated snapshots, but as ongoing patterns in temperature, wind, and atmosphere. Mars Pathfinder landed in 1997 and restarted surface exploration after a long gap. Its success helped renew public excitement and showed that Mars missions could once again place active hardware on the surface of the planet. Pathfinder deployed the small rover Sojourner, which became the first rover to operate on Mars. Though tiny by later standards, it proved that a mobile robot could explore the Martian surface and investigate more than one fixed point. Spirit and Opportunity landed in January 2004. These twin rover missions became some of the most beloved explorers in space science, partly because they lasted so long and returned such a large and meaningful record of Mars. Their mission objective was to look for signs of past water. This goal was central because water is one of the most important clues when trying to understand the history of Martian climate and the possibility of past habitable environments. Spirit and Opportunity were identical twin robots. Using two similar rovers in different locations allowed scientists to compare regions of Mars more directly and to broaden the search for geological evidence of water. The results helped rewrite scientists' understanding of early Mars. The rovers found strong evidence that water had once affected the planet's rocks and soils in important ways, making Mars's ancient past seem more dynamic and more complex. Opportunity survived far beyond its planned lifetime and explored Mars for years longer than expected. Its long mission turned it from a short-term visitor into a patient field geologist, steadily adding detail to the story of the planet. Curiosity landed in Gale Crater in 2012. This rover was larger and more capable than earlier ones, and it was sent to investigate a place that seemed especially promising for understanding ancient Martian environments. Curiosity's landing used the Sky Crane system, which lowered the rover on cables during the final descent. This engineering method was dramatic and highly precise, designed to place a large rover safely onto the Martian surface in a controlled way. Curiosity was designed to assess whether ancient Mars could once have supported microbial life. That did not mean the rover was sent to find living creatures directly, but to determine whether past conditions were suitable for life on a small scale. Curiosity found strong evidence that Gale Crater once contained lakes and habitable environments. That result was important because it showed that at least some parts of Mars were not merely damp for a moment, but capable of sustaining stable watery conditions. Curiosity showed that some Martian sediments were laid down in calm water rather than only in violent floods. This matters because calm water suggests quieter, longer-lasting environments where fine layers could build up gradually over time. The rover has climbed through layered deposits that preserve a long environmental record. As it moved upward through these rocks, it was in effect traveling through chapters of Martian history, reading changes in climate and chemistry layer by layer. Curiosity helped document seasonal and daily changes in the thin Martian atmosphere. So even while studying ancient rocks, the rover also became an observer of the present-day rhythm of the planet's air and weather. Curiosity captured blue sunset images that became some of the most recognizable views from Mars. These pictures were visually striking, but they also helped show how dust and light interact in the unusual Martian atmosphere. The rover continues to show that Mars exploration can produce both geology and atmospheric science from the same mobile platform. Curiosity is not just a rock investigator or just a weather station. It is a mission that blends multiple kinds of science in one continuing journey. Gale Crater's central mound, called Mount Sharp, acts like a natural layered archive of changing Martian conditions. Each layer offers clues to what the environment was like when that material was laid down, making the mountain a kind of geological memory. InSight landed on Mars in 2018. Unlike the rovers, it was not built to drive across the landscape, but to remain in one place and listen carefully to the planet beneath it. Its name stands for Interior Exploration, using seismic investigations, geodesy, and heat transport. The name itself reflects the mission's purpose, which was to understand Mars from the inside out, rather than mainly from the surface downward. InSight's main goal was not to travel, but to stay still and listen for activity inside Mars. That stillness was part of its strength, because a fixed and sensitive lander could detect tiny motions in the ground with great precision. The mission revealed the internal structure of Mars in a way no previous mission had done. Before InSight, much of the planet's interior was estimated indirectly, but afterward scientists had far stronger evidence about what lies below the crust. InSight's data showed that the Martian core is liquid. That discovery helped reshape the planetary picture of Mars by confirming that deep inside the planet there is still a molten metallic region rather than a fully solid center. It also showed that the crust is layered beneath the landing site. This finding matters because a layered crust suggests a more complicated history of formation, cooling, burial, and change than a simple single-shell model would imply. InSight detected seismic waves from meteoroid impacts as well as from marsquakes. That meant the lander could study both internal geological activity and sudden outside events that shook the ground. Studying those seismic signals lets scientists estimate where quakes happened and what materials the waves passed through. In this way, each vibration becomes a kind of messenger, carrying information from hidden parts of the planet. InSight proved that even a planet often described as geologically quiet still contains measurable internal activity. Mars may not be as active as Earth, but it is not completely still, and the mission demonstrated that clearly. The mission changed Mars from a mainly surface-mapped world into a planet with a measured internal anatomy. Instead of only seeing its outer shape, scientists could begin describing the deeper structure that supports the visible planet above. Perseverance landed in Jezero Crater in February 2021. This mission was chosen for a site believed to preserve an ancient river delta, giving the rover access to one of the most promising records of past water on Mars. Perseverance is larger and heavier than Curiosity. That extra size supports additional tools and sampling systems, allowing the rover to do more detailed work while building on the success of earlier missions. NASA says Perseverance has about 3 centimeters more chassis length than Curiosity. That may sound like a very small difference, but it reflects the careful engineering choices made when adapting an already successful rover design for a new mission. NASA also says Perseverance is about 126 kilograms heavier than Curiosity. That extra mass includes new hardware and sample handling systems, showing that Perseverance was built not just to study Mars, but also to prepare for what may come next. The rover's mission includes studying an ancient delta environment. Deltas are especially valuable because flowing water brings in sediment from different places, and those sediments can store a rich record of local environmental history. Perseverance is also designed to collect and cache selected rock samples for possible return to Earth by future missions. This is a major step forward because laboratory study on Earth can be far more detailed than what current rover instruments can do alone. Jezero Crater was selected because it records a place where water once carried sediment into a crater basin. That makes it a natural site for layered deposits that may preserve chemical and textural evidence from a wetter time. Perseverance carries instruments that can analyze rocks, textures, and chemistry at very fine scales. These tools help scientists look closely at the structure and composition of samples, searching for clues about ancient environments. The mission builds on engineering heritage from curiosity while adding new science tools and sample tubes. In other words, Perseverance is not a completely separate experiment, but an improved descendant of earlier rover designs. Perseverance's landing expanded Mars exploration from simply assessing habitability toward preparing samples for deeper laboratory study. That shift is important because it connects robotic fieldwork on Mars with future hands-on analysis back on Earth. Ingenuity traveled to Mars attached beneath Perseverance. The little helicopter reached the planet as a companion to the rover, tucked safely underneath during the long journey through space and the dangerous landing sequence. Ingenuity was an experimental Mars helicopter rather than a science rover. Its main purpose was not to study rocks or collect samples, but to prove that powered flight could work in the very thin Martian atmosphere. Its original purpose was to test whether powered flight was possible in the extremely thin atmosphere of Mars. That question mattered a great deal because flying on Mars is much harder than flying on Earth, and a successful test would open a completely new way of exploring another planet. Ingenuity achieved the first powered, controlled flight on another planet. This was a historic milestone in exploration, not just because the helicopter rose into the air, but because it proved that human engineering could create true aircraft operations in an alien world. The success of the helicopter turned what began as a small engineering demonstration into a much longer and more ambitious campaign. Instead of completing only a few brief test flights and stopping, Ingenuity kept operating and showed it could continue contributing useful observations. Ingenuity showed that aerial scouting could help future Mars missions plan routes and inspect terrain in advance. A flying vehicle could look ahead at obstacles, slopes, and pathways, in a way a ground rover cannot easily do from its lower viewpoint. The helicopter also photographed Perseverance's landing hardware from the air. This gave scientists a new perspective on the parts used during entry, descent, and landing, helping them study how that complex arrival sequence had unfolded on the Martian surface. One of those aerial surveys documented the rover's parachute and backshell after landing. Images like these are valuable because they let engineers examine mission hardware in its final resting place and learn more for future landings. Ingenuity demonstrated that even in very low air density, flight is possible if the aircraft is extremely light and its rotors spin fast enough. In simple terms, Mars does not make flight impossible, but it demands a very different balance of weight, lift, and speed. Mars exploration is no longer limited to orbiters and surface vehicles because Ingenuity added the air to that list. That small helicopter expanded the way humans can work on another world, showing that Mars can be explored from above as well as from orbit and from the ground. Mars Express began science operations in 2004. Since then, it has remained one of the most important long-lived orbital missions of Mars, steadily adding detail to our understanding of the planet over many years. The mission has produced detailed three-dimensional views of Mars. These views matter because they do more than show where features are. They help scientists understand height, depth, slope, layering, and the true shape of the landscape. Mars Express provided one of the most complete maps of the chemical composition of the Martian atmosphere. That kind of mapping helps scientists understand what the air is made of, how it changes, and how Mars has evolved over time. It has studied Phobos in unprecedented detail. This close work matters because Phobos is not only one of Mars's moons, but also a clue to the history of small bodies and the formation of the Martian system. Mars Express helped trace the history of water across the planet. By studying minerals, surface patterns, and subsurface clues, the mission helped show that water on Mars once played a much larger role than it does today. The mission found evidence for minerals that require water to form. This is important because such minerals act like fingerprints left behind by water, allowing scientists to identify places where liquid water once interacted with the rocks. Its radar instrument, MARSIS, detected widespread subsurface water ice. That discovery showed that Mars hides large frozen reserves below the ground, not just at the visible polar caps, making the planet's water inventory richer than the surface alone suggests. Mars Express results suggest that some volcanism on Mars may have persisted until geologically recent times. If that is true, it means Mars may not have shut down all volcanic activity as early or as completely as once imagined. The mission also helped clarify that some unusual equatorial deposits may hide major ice reserves. This was especially interesting because ice near the equator is less expected and could be more useful for future exploration than ice buried only at the poles. Mars Express shows how long-lived orbiters can keep making important discoveries decades after launch. A mission does not always reveal all its value quickly. Sometimes years of careful observation uncover patterns that short missions would never have seen. The ExoMars Trace Gas Orbiter studies trace gases and atmospheric chemistry at Mars. Trace gases are present only in tiny amounts, but they can reveal active processes that would otherwise remain hidden in the background of the larger atmosphere. This orbiter detected hydrogen chloride in the Martian atmosphere. That detection was notable because hydrogen chloride had not previously been confirmed there, adding a new piece to the puzzle of Martian atmospheric chemistry. It was the first time hydrogen chloride had been detected on Mars. Discoveries like this matter because they show that even now, with many spacecraft already having studied Mars, the planet can still surprise scientists with previously unseen chemical behavior. ESA linked the hydrogen chloride detection to a cycle involving salty dust, sunlight, and water vapor. In other words, the gas may have been produced not by one isolated source, but by a larger environmental interaction between surface material, light, and atmospheric moisture. This means parts of Martian atmospheric chemistry are tied directly to dust-lifting events and seasonal water movement. So when dust rises and the water cycle shifts, chemistry in the air can shift as well. Trace gas studies matter because tiny atmospheric constituents can reveal active chemical processes, even when the bulk atmosphere seems fairly stable. Very small amounts of gas can point to larger systems of interaction that would otherwise be easy to miss. The orbiter has also contributed to understanding how Mars loses water over time. This is one of the major questions in Martian science, because the loss of water is deeply tied to the planet's long transition from wetter conditions to the dry world seen today. Atmospheric water loss is not just a simple matter of evaporation. It also includes the transport of water-related particles to high altitudes, where atoms can eventually escape into space and be lost from Mars for good. ExoMars observations support the idea that Mars is still chemically and climatically active, even though it has no large modern seas. The planet may look quiet, but its atmosphere and surface still participate in ongoing cycles and reactions. The combination of orbiters from different agencies has made Mars one of the best monitored planets beyond Earth. With multiple spacecraft studying it from different angles and with different instruments, Mars is observed as a system rather than as a mystery glimpsed only occasionally. Mars has no planet-wide magnetic field today, but parts of its crust are magnetized. These regions are like leftover traces of an earlier time, preserving evidence that the planet once behaved differently deep inside. Those crustal magnetic patches suggest that Mars once had a stronger internal dynamo in its early history. A dynamo is the deep planetary process that can generate a global magnetic field, so these patches hint that Mars once had more protection from space weather than it does now. Because Mars lacks a strong global magnetic field today, solar activity can interact with its atmosphere more directly than it does on Earth. That stronger exposure helps explain why Mars has lost so much of its air over very long periods. This also helps explain why Mars can have auroras without having an Earth-like global magnetic shield. The process is more complicated and regional, shaped by local magnetic remnants and direct atmospheric interaction with solar particles. Mars's magnetism is therefore patchy and regional rather than simple and planet-wide. Instead of being wrapped in one broad magnetic shell, the planet seems to carry scattered magnetic memories in parts of its crust. The crustal magnetic record is one reason Mars is so useful for studying how terrestrial planets evolve differently. It gives scientists a chance to compare a world that lost its strong global field with one like Earth that kept it. Planetary scientists can compare Mars and Earth to ask why one planet retained a thicker atmosphere and a strong magnetic field, while the other largely lost both. This comparison is one of the most important ways Mars helps us understand Earth as well. Mars is a key example of how habitability can change dramatically over billions of years. A planet that may once have had more favorable surface conditions can, over time, become far colder, drier, and harsher. The planet preserves a story of past climate, partly because erosion is often slower there than on Earth. Since Mars lacks many of the strong erosive forces that constantly reshape Earth, ancient features can survive for much longer. That preservation makes Mars a valuable archive of early planetary history. Old surfaces, ancient channels, and long-exposed rocks remain available for study, offering scientists a clearer window into very ancient times. The soil and dust of Mars contain oxidized iron minerals that contribute to the planet's red color. This is why the world appears reddish from afar, and why its most famous nickname has remained so fitting for so long. Martian regolith is often described as soil in mission materials, but it is not soil in the biological Earth sense. It lacks the living ecosystem, organic richness, and complex biological activity that make soil on Earth part of a living system. Dust is so important to Martian surface conditions that it affects solar power, visibility, heating, and atmospheric chemistry all at once. A single dust event can influence engineering, weather, lighting, and long-term atmospheric behavior. Some dust devils have even cleaned rover solar panels, unexpectedly extending rover operations. In those cases, a natural Martian weather event briefly became a kind of helpful maintenance system for human-made machines. Other dust events have ended missions by blocking sunlight from solar-powered spacecraft. So the same dusty environment that can occasionally help a rover can also become a mission-ending problem when too much sunlight is cut off for too long. Mars's dust grains are fine enough to stay aloft and color the sky, but also abrasive enough to matter for engineering design. That means dust is not only a visual feature, it is also a practical challenge for machines meant to survive on the planet. The thin atmosphere of Mars means wind must behave differently there than on Earth to move the same-sized particles. Yet despite the low air pressure, Mars still manages to transport sand and dust in ways that visibly reshape the land. Even so, Martian winds and vortices clearly reshape dunes and lift dust regularly. This shows that modern Mars is still active on the surface, even without flowing rivers or dense air. The red color seen from space is therefore both a surface property and an atmospheric effect. The iron-rich materials on the ground matter, but the dust suspended in the air also helped shape the planet's overall appearance. A close look at Mars always reveals a more varied palette than the simple nickname Red Planet suggests. Browns, golds, tans, and dusty pink tones all appear across the surface and sky, making Mars visually richer than its label implies. Mars is struck by enough meteoroids that fresh impact craters can still appear in modern times. The surface is not only ancient, it is also still being marked by new events as space rocks continue to reach the ground. Those modern impacts can be especially useful because they send seismic waves through the planet that landers like InSight can detect. In that way, a sudden collision at the surface can become a valuable experiment for studying the hidden interior of Mars. Mars also sends pieces of itself to Earth in the form of meteorites blasted off its surface by large impacts. These rare Martian rocks give scientists a direct way to study part of the planet in laboratories on Earth, which is remarkable when you remember that Mars is millions of kilometers away. Some of the best laboratory evidence for Martian rock chemistry was studied on Earth long before rovers could carry equally advanced instruments across the surface of Mars. That means scientists were learning about the planet not only through telescopes and spacecraft, but also through actual fragments of Mars that had fallen here. Martian meteorites allow scientists to compare laboratory samples with what orbiters and rovers observe on the planet itself. This kind of comparison is very useful because it helps connect close-up chemical testing on Earth with the broader geological picture seen directly on Mars. Impact craters on Mars can expose buried layers, almost like natural cuts through the crust. When an impact digs into the ground, it can reveal older material that had been hidden below the surface for a very long time. Because erosion is often slower on Mars than it is on Earth, many impact features remain visible for extremely long periods. This allows ancient structures to survive as readable pieces of the planet's history rather than being quickly worn away. Large impacts were important not only for damaging the surface, but also for shaping the deeper interior of Mars in its early history. The effects of these giant collisions may have reached far below the crust and influenced how the planet developed internally. Some impact basins may have influenced later volcanic, tectonic, or sedimentary evolution on Mars. In other words, a very ancient collision might have changed what happened in that region long afterward, guiding later geological activity. Mars records both the violence of early solar system bombardment and the quieter geological changes that followed. The planet preserves signs of both sudden catastrophe and slow transformation, which makes its history feel layered and deep. Mars is one of the main world scientists study when asking whether life ever began beyond Earth. It is close enough to explore in detail, and it shows strong evidence that conditions were once more favorable than they are now. The strongest reasons for that interest include ancient water, possible energy sources, and rocks that have remained preserved for long spans of time. Together, those features make Mars one of the most promising places to study the ancient ingredients of habitability. Modern Mars is harsh at the surface, with cold temperatures, low air pressure, and high radiation exposure compared with Earth. Any living thing at the surface today would face a much more difficult environment than life usually faces on our own planet. For that reason, the best places to preserve signs of ancient life would likely be old sediments, mineral-rich deposits, or protected subsurface environments. These settings can shield delicate chemical traces and hold onto evidence longer than open, exposed ground. Rovers such as Curiosity and Perseverance are therefore not searching only for life itself, but also for environments that could preserve signs of past life. This is a careful and realistic strategy, because preserved evidence may be easier to find than direct proof of life. Clay minerals and certain salts are especially important because they can form in water and can trap evidence of past chemistry. These materials can act almost like natural storage spaces, keeping a record of what ancient environments were like. Ancient lake beds on Mars are especially valuable because fine sediments can bury and preserve records gradually over time. Quiet water allows layers to settle gently, and those layers may hold some of the clearest clues to Mars's past. Jezero Crater's delta is important for exactly that reason. Deltas gather sediments brought in by flowing water, salt them, spread them out, and can preserve a rich record of what once moved through the system. Gale Crater is important for a different reason, because it preserves a long stack of changing environments in one place. Instead of showing just one watery setting, it records a sequence of conditions that changed over time. Mars research often focuses on habitability, preservation, and detectability as three separate questions rather than one. A place may once have been suitable for life, but that does not automatically mean it preserved clear evidence, or that current instruments can detect that evidence easily. Human exploration plans pay close attention to Martian water ice because it could support life support systems and fuel production. Ice is therefore not only scientifically interesting, but also potentially practical for any future long-term presence. Accessible subsurface ice is especially valuable because it could be easier to mine than more deeply buried reserves. The easier it is to reach water, the more useful that location becomes for exploration planning. NASA studies divide Martian water resources into categories such as ground ice, hydrated minerals, and possible deeper groundwater. This helps scientists think more clearly about what kind of water exists, where it is, and how difficult it would be to use. Not all forms of water on Mars are equally useful for future explorers. The exact location, depth, concentration, and physical form of the water all matter when deciding how valuable a particular reserve might really be. Dust, cold, radiation, and low air pressure make Mars difficult for astronauts, even though it is one of the more accessible planets. The challenge is not simply getting there, but surviving and working safely once people arrive. The same thin atmosphere that offers too little pressure protection also provides too little aerodynamic braking for simple landings of heavy payloads. This makes Mars a surprisingly difficult world for engineering because it does not help spacecraft slow down very much. That is one reason Mars landings are considered especially challenging. The atmosphere is thick enough to create heating during entry, but too thin to slow heavy spacecraft easily, which places landers in a difficult middle condition. Robotic missions to Mars therefore double as technology tests for eventual human missions. Every landing system, sampling tool, weather record, and environmental measurement can help prepare for future people on the planet. NASA's broader Mars exploration program explicitly links robotic science with future human exploration. The goal is not only to learn about Mars as a scientific object, but also to understand how humans might one day work there safely. Mars remains central to human exploration planning because it is scientifically rich, comparatively reachable, and preserves evidence of planetary change. Few worlds offer such a strong combination of practical interest and deep scientific value. Mars's thin atmosphere allows more meteoroids to reach the ground than Earth's thick atmosphere does. On Earth, many smaller incoming objects burn up before impact, but Mars provides less protection in that way. Because Mars lacks active plate tectonics like Earth's, many ancient surfaces remain in place much longer. This means the planet often preserves very old geological records that would have been erased or deeply altered on Earth. The giant shield volcanoes of Mars could grow so large partly because Mars has lower gravity than Earth. With less gravitational pull, these enormous volcanic structures could build upward and outward to astonishing sizes. Lower gravity also helps volcanic edifices stand taller before their own weight causes collapse. That is one reason Mars can host mountains and volcanoes whose scale feels so extreme when compared with Earth. The crust of Mars records both volcanic construction and later gravitational spreading in some giant volcano deposits. Even after a volcano forms, its immense weight can continue changing the surrounding landscape. The phrase "dead planet" can be misleading when applied to Mars, because its atmosphere still circulates, its dust still moves, and its interior still produces quakes. Mars may be quiet compared with Earth, but it is not inactive in every sense. Mars is cold and dry today, but it is not static. Winds still blow, frost still shifts with the seasons, impacts still occur, and the atmosphere still changes in ways spacecraft can measure. Long-lived orbital missions keep discovering things older models did not predict, such as unexpected trace gases or buried ice in surprising places. Mars continues to remind scientists that a planet can remain full of unanswered questions even after decades of study. The modern scientific picture of Mars is therefore a story of revision, not of one final settled answer. Each new mission tends to refine, complicate, or sometimes overturn what earlier data seemed to suggest. Mars remains one of the few planets where geology, climate, atmosphere, and astrobiology all overlap so strongly within one exploration program. It is a world where many branches of science connect naturally to one another. Mars exploration has been continuous in one form or another since the Pathfinder era began the modern sequence of missions in 1997. Since then, the planet has rarely been left entirely unobserved for long. Since that period began, Mars has often had more than one active spacecraft studying it at the same time. This overlapping presence has made it possible to compare different kinds of data gathered at the same moment. That overlap allows scientists to connect surface observations, orbital mapping, and atmospheric measurements. A rover may describe local conditions, while an orbiter shows the wider regional picture around it. A dust storm seen from orbit can be compared with weather and lighting changes recorded by a rover on the ground. This gives scientists a fuller understanding of how a single event looks from above and how it feels at the surface. An impact spotted from orbit can also be compared with seismic data from a lander. That kind of cross-check is especially valuable because it ties a visible surface event to a measurable internal response. Mineral detections from orbit help mission planners choose landing sites that rovers can later examine directly. In this way, orbital science often acts as a guide, pointing surface missions toward the most promising places. Mars is therefore one of the best examples of a planet explored as a coordinated system, rather than by isolated single missions. Different spacecraft support one another, and the combined picture is much richer than any one mission alone could provide. The scientific importance of Mars comes partly from how many different methods can be applied there at once. Remote sensing, ground imaging, chemistry, seismology, atmospheric analysis, and aerial scouting can all contribute to one shared story. Every major Mars mission has relied on results from earlier missions when choosing targets, tools, and questions. The exploration of Mars has grown step by step, with each mission building on what came before. Mars is a world where exploration history is layered almost as clearly as the rocks themselves. The story of how humans have learned about the planet has accumulated in stages, just like the geological history the missions study. Its two tiny moons are so unusual that they may someday help explain how small bodies become captured or reassembled around planets. Their odd shapes and uncertain origins make them important beyond the Mars system itself. Mars remains a world of contrasts. Ancient but still changing. Quiet yet active. Dry today yet marked everywhere by the memory of water. The more carefully it is studied, the more it seems to hold both simplicity and mystery at the same time. And so the picture of Mars becomes softer and broader the longer we look at it, with dust moving through thin air, old rocks keeping their long memory, and small machines wandering gently across a silent red world.